Just to remind what we do, we are at the hackathon. And if you don't know where to find the bounty that Neon EVM has, this is the Taikai page where you can find it. Just click on Neon EVM. And this is the description of the bounty if you haven't seen it yet. So the task will be to create a DeFi use case of Neon EVM's composability libraries that I'm going to talk about today. And we see DeFi in the broadest sense possible. Whenever you're going to interact with Solana through composability libraries created by Neon EVM, you will probably face with the SPL tokens. And whenever you interact with the SPL tokens, we see it as a DeFi use case. So whatever you create with the composability feature is going to be OK to submit for this bounty task. And so the task will be to create a use case using these composability libraries. And some of the examples are a cross-chain lending or borrowing platforms. These are Clear DeFi, a composable Radium AMM, a arbitrage bot, for example, or an ERC24SPL launcher. ERC24SPL is a hybrid token created by Neon EVM, which is a wrapper, a Solana wrapper for ERC20 token. And you can go about it by either looking at the examples that we provide in our repos, and you can find them here under Neon POC repo. And this is the one. Here you can simply start by forking one of these repositories. And if you want, for example, a memecoin launchpad use case, or if you want to replicate a flash loan use case, then these are the ones that we can get you started with this repository. And so basically, yes, you can start from here, and you're going to have a working start of this composability use case. We also have an NPM package, which you can simply install and start working from there. But all this is about composability created by Neon EVM to link Ethereum and Solana. And let me go right into that by talking, yes, about Neon EVM first. So this was just a kind of an organizational introduction to what you can do in this hackathon. And Neon EVM is a Solana network extension that breaks the runtime barrier between EVM dApps and Solana. So at Neon EVM, we try to take the best of the two ecosystems and take the EVM benefits, which are for EVM developers. Obviously, that the Ethereum RPC compatibility is available, all the familiar tooling and all the languages that they know are available for them to use to be able to connect to Solana's liquidity and user base through Neon EVM. So we take the best of the two worlds. From Neon EVM, everything is known and familiar, and you can use Ethereum RPCs. And from Solana, we take parallel execution, low gas fees, and of course, users, a growing Solana ecosystem. So what you might think that Neon EVM might have something to do with bridges or rollups, but it couldn't be further from the truth. Neon EVM is a Solana network extension. It's a program on Solana, in other words, and it consists of two main things, Neon Proxy and Neon EVM program. Neon Proxy prepares the transactions off-chain. It wraps Ethereum-like transactions into Solana-style transactions by adding them mostly into the data field of the Solana transactions. It provides Ethereum RPCs, and basically it prepares this transaction that goes into Solana. And when it goes into Solana, it hits the Neon EVM program. Neon EVM program picks this transaction up and executes this transaction directly and natively on Solana without bridges or without anything else. So it's just, since it's just an EVM, a virtual machine on Solana, it can do this directly and natively, so there is no overhead. And yeah, this is what I was talking about. So the Ethereum-like transaction with nonce, with the gas price, with the values and the data, goes directly into the data field of a Solana transaction. And Neon EVM also packs the address list into the program index and the accounts list into the accounts list section. So under the hood, Neon EVM also creates all these accounts that are needed for a Solana transaction to go through. As you probably know, the accounts are a whole big thing on Solana. Unlike Ethereum, where we have an externally owned account and contracts, on Solana, basically everything is an account. Token is an account, balance is an account. So everything should go into the accounts list. And one of the things that Neon EVM does, thanks to this composability feature that I'm going to talk about, is create all these accounts that are needed for Solana to execute transactions and packs them into this Solana-style transaction in the accounts list. So how does it do that? Neon EVM has a composability feature, which includes composability libraries and precompiled contracts that abstract away all this complicated Solana architecture, including these accounts. And basically, these are the libraries that are available at the moment, and they help EVM projects interact with these Solana programs. So these are native and custom Solana programs that you can interact with from EVM dApp if you use composability libraries. And these libraries, they're all called the same as these Solana programs. So the system program library, the SPL token program library, the associated token library, and also Metaplex and Radium libraries. And with these composability libraries that you import into your smart contracts that you write in Solidity, you can access all these Solana programs. And so the composability feature also consists of precompiled contracts that help us execute the transactions on Solana, in Solana runtime. And these composability precompiled contracts are different. We have several ones, but this one is the main one. So if you are going to build with composability feature, you are going to execute your transactions through this precompiled contract, which first of all prepares a list of addresses with a payer account and Solana addresses for a Neon address that corresponds to the Neon address, and is going to mainly execute the instruction with a call to Solana and return the data on this instruction. But I'm going to show you an example a bit later. This is just the interface for the main precompile that we are going to use. These precompiles, basically they allow you to access Solana state, create accounts, and execute transactions on Solana. And this is, again, happens through the iCall Solana precompile. And another thing, with this precompile, you can batch, you can pack several functions into several instructions. For example, like here for deploying a new SPL token and minting it on Solana into a batch and send it as one transaction through Neon EVM. And as for composability libraries, these are the things that composability libraries contain, and they are all built in the same way. They are going to have a file, a file with the helper functions that are going to format the instructions in a specific way that Solana expects them. Then there is a file with the getter functions where you can pull the data to get into your front end, for example. And then there are custom errors so that you can handle the errors and debug. And on Solana, it's done usually completely different, but here with this library, you're going to get errors that you can actually handle from Solidity contracts. And also there are Solana constants for program IDs, account public keys, and accounts for rent management. You don't have to deal with Solana's system for rent management because one of these libraries also calculates the rent exempt fee that you're going to get for 2 years. And yeah, basically you don't need to go into Solana architecture and think about the accounts. You don't need to think about the rent, but because this all happens within composability libraries. And the flow is going to be very simple. You have a caller contract where you import a composability library, or rather many composability libraries at the same time. And from that, you send a call to a precompiled contract I call Solana, which natively executes the instructions. And the caller contract is an account owned by new EVM program on Solana. So the ownership is going to be within this contract. And later, when I'm going to show you how to deploy an SPL token, we are going to keep ownership within the caller contract. Then you can obviously delegate the ownership and pass the ownership to another account. But when we are talking about this cluster of functions, this cluster of instructions, at this point, the owner is the contract. Then it can request a payer account to pay for execution costs on Solana. As I've told you before, rent is going to be covered from the payer account, and the contract is going to request that, but it won't have to calculate it manually. Then the contract owns the accounts created on Solana. All the system accounts, token mints, are going to be owned again by this account, by this contract. And yes, it must implement authentication logic to manage access to those accounts. And about the current libraries, as I've told you before, we have 5 of them, and 3 are communicating with the native Solana programs, and one of them, libradium program, communicates with Radium DAX. So if you're building a DeFi use case, that's probably the one you're going to be most interested in. And if you're going to be launching, for example, a meme coin launchpad, starting from the example in our libraries and in our GitHub repositories, then you'll be able to connect to Radium CPMM pools with concentrated liquidity, which are basically the same thing as Uniswap v3. So if you have an idea for Uniswap v3, you can basically do the same thing on Solana using this libradium program library. But now I want to spend several minutes talking about the SPL token program library, because it's kind of the basis of what's going to happen if you interact with SPL tokens from Solidity contracts using the composability feature. So you have these basic instructions to interact with the token. You can mint, you can transfer, you can approve or revoke authority, burn and close account. And an example for interacting with this SPL token library for the caller contract would be a very basic contract with a transfer function here, where you basically derive the PDA account from the address, from the Ethereum address that you provide with a message sender. Then you derive the sender's token account from the sender account and the token mint account. So everything is an account, even tokens. That's why we need to derive this many accounts. Then you format instructions with the sender, recipient, and amount. Then you basically build the instruction, prepare and build, and execute with the call to iCall Solana precompile. And when you're going to open the composability libraries GitHub repo, you're going to see these examples of call contracts to different programs on Solana. They are all formatted and they're all structured in the same way, where you basically get the accounts, you build the instruction, and you send the instruction to the precompile. Now, this is an example of how to deploy an SPL token on Solana using Hardhat. So yeah, a good thing about new EVM is that you can use all the familiar EVM tooling, including Hardhat, and write in Solidity. And here is how you deploy an SPL token. Here we actually deploy this caller contract, which has an imported SPL token library and all these functions for deploying the token, and we basically just specify the seed and the 9 decimal precision, which is typical to Solana, and with the method create initialize token mint, we pass the same seed that we passed before, and basically we call this caller contract, and we deploy the mint, deploy the token. And then once we deploy the token, we need to create an account that's going to hold this token. And as I've told you before, the ownership is at the new EVM program. That's why we leave the owner field empty. We zero it out at the first and the second row. And we get the neon address and the arbitrary token account to which we are going to send this token. Which is going to own this token mint. And then once we have the token and once we have the balance that is going to hold these tokens, we can go ahead and mint actual tokens to this balance account. And we do this with a seed that we provide before. Then the recipient token account, it's not a transfer, so this means that recipient is just the token account that we just created, and an amount. And basically the same functions, but the same function only for transfer. We use the transfer method with a token mint field, a recipient, and an amount to transfer. So this is all very simple, and basically, this is how you can deploy a token and mint tokens to an account using a composability library. And I've told you that we have these repositories with the libraries and the caller contracts. So this is one of those libraries where, yeah, these are all of them actually. And here you can see this call SPL token program caller contract, which we just looked at the snippets from it. But here you can see that it gets all these helper libraries. Oh, it's too small. Okay. And the iCall Solana precompile. And then we just create this token mint. Then we build the instruction. The contract bit. Yes, we prepare the instruction and execute it through the iCall Solana precompile. And the same for each of the functions that we are going to have here. So again, for the initializing arbitrary token account to which we've sent the mints, again, we first define the owners, we define the accounts, then we build the instruction, we format it with the help of these methods that we get from the libraries, and we send the instruction to the iCall Solana precompile. So this is going to happen for every one of these functions. So basically, as you can see, you write Solidity code with the same functions that you would do normally for an EVM app, but by sending the instructions to the iCall Solana precompile and using the libraries to format the instruction, you send them to be executed on Solana. I think this is all I wanted to tell you. And again, this is where you can find the bounty task for this thing. And don't hesitate to contact me. I hope I'm gonna be able to tell you in more detail everything about this composability feature. Thank you so much for your time and attention. I hope you have a great day.